Okay, assalamu alaikum, guys. Today we will continue on chapter 11, okay, the refrigeration cycles. We didn't have a tutorial in refrigeration cycles last week since you had a midterm. Okay, I hope you did well in it. And yeah, this chapter is like you'll find it trivial if you do understand pretty much most of the things in the previous chapters. Because again, it's the same thing, just a cycle. And you go from a point to a point and understand each device in the cycle, how does it operates, and then, yeah, you solve the cycle and that's it. Even in the refrigeration cycle, we have some simplification because we have the throttling device, which have a constant edge across the device. So you will not need, or you don't need to do any calculations across the throttling device because the enthalpy already there is constant. So we have the typical vapor compression cycle, and we have two innovative cycles or modification of the vapor compression cycle, the cascaded cycle and the multi-stage cycle. And yeah, and we also have gas or gas refrigeration cycles. Okay, mainly we will have the normal Brighton one. But even though uh, if it was Brighton with regeneration, you should be able also to do it. Okay, because again it's the same principle, just now for refrigeration. That's it. Okay, let's start by the normal one. What do we have here? Okay, let me enlarge it. One doesn't enlarge. Okay, hope you can see it well. We have, okay, oh, let me select this one. We have a commercial refrigerator with refrigerant 134A as the working fluid. Is used to keep the refrigerated space at minus 30 degrees Celsius. So this is the temperature that we need to maintain the refrigerated space at by rejecting its waste heat to the cooling water that enters the condenser at 18 degrees Celsius. So this is, here we have the condenser. This is the condenser. And the condenser is water cooled, okay? So we have here that it rejects the waste heat to a cooling water. So this is the inlet of the cooling water, and this is the outlet of the cooling water. Okay, what is the temperature? Okay, that enters the condenser. It enters here at 18 degrees Celsius and it exits at 26 degrees Celsius. Okay, so this is water. And we have the flow rate of this water, which is 0.25 kilograms per seconds. Yeah, and the refrigerant enters the condenser at 1.2 megapascals. So this is um, the condenser pressure, let's call it, okay? So this is the pressure across the condenser, which is 1.2 megapascals. And 65 Celsius, which is the inlet to the condenser, yeah? So here, at this point here, we have the temperature to be 65 Celsius. What else we have? And it leaves at 42. So this is the leaving temperature, which is 42 degrees Celsius, okay? And this is 42, this is 65. And now the inlet to the compressor is 60 kilopascals. So the lower pressure or the evaporator pressure, okay, evaporator pressure is 60 kilopascals. And we'll also have, okay, and here's our compressor, okay. There's our compressor. Yeah. And what else? Compressor 60 kilopascals, and the compressor is estimated to gain a net heat of 450 watts from the surrounding. Okay, so we are expecting to have an increased amount of heat of 450 watts from the surrounding. Okay. What else we have? The net state of, or the inlet state of the compressor, 60 kilopascals, and here, yeah, minus 34 degrees Celsius. The compressor is estimated to gain the net heat. Okay, we will have this value. Determine now the quality of the refrigerant at the evaporator inlet, the refrigeration load, and also the COP of the refrigerator and the theoretical maximum refrigeration load for the same power input to the compressor. Okay, of course you will have here constant H and the pressure is the same. So what is the first thing that we need? We need to calculate the quality of the refrigerant at the evaporator inlet, which is of course this point. We need to find X at this point. Now, can we find H at this point, X at this point? Yeah, of course. We have the upper pressure, okay? So H of this point, which is, I'll now call the points. This is point 1, mainly before the compressor. This is point 2, and this is point 3, and this is point 4. So at point 3, we have H3, okay, is equal to, what is the pressure that we have? We have the pressure is 1.2 megapascals. And we have the temperature to be 42 degrees Celsius. So now go to the tables. And I'm going now to the tables, and I'm going to table A12 because I have pressure. You can go also to table A11. And I can see that 1,200 kilopascals, 1,200 kilopascals, in fact, have a saturation temperature of 46.2. Okay, so Tsat at this pressure, Tsat at this pressure is equal to 46.29 Celsius. Okay, so this is Tsat. And since we have temperature that is lower than Tsat, what is the state? It is subcooled, yeah? So it is subcooled liquid. Now, for subcooled liquid, we can use HF at temperature, which is equal to 42 degrees Celsius. Okay, now what is HF at the temperature is equal to 42 degrees Celsius? I'm going to the 42 degrees Celsius, and I can find here, okay, I'm going 42 degrees Celsius. I have the H as 111.26, okay? So 111.26. 111.26 kilojoules per kilograms. Okay. Now what should I do? I just fix H, okay? So from 3 to 4, enthalpy is constant, so H4 is equal to H3, which is equal to 1.26 kilojoules per kilograms. And how can I know the quality here? I have the evaporator pressure, okay? So pressure 4 is equal to 60 kilopascals. Now go check this enthalpy with this pressure, see what is the X that you have there. Of course, you're gonna find that the H is between HF and HG at that pressure, but we need to know the X exactly at that point. So I'm going again, okay, follow me. I'm going to table, the table that contains the pressure, which is A12. From A12, I go to 60 kilopascals, sorry. So for 60 kilopascals, I can see that Hg is equal to, Hg for 60 kilopascals is equal to 278.46, okay? So 278.46, and HF at that pressure is 3, or how much? Oh, sorry, I'm going to a temperature, pardon me. 60, yeah, so 60. Okay, let me delete. Yeah, I was checking with 60 degrees Celsius. I want to check with 60 kilopascals. So HF is 227.79, and HF is 3.841. Okay, so this value is between. So how to find the X? I have the equation that tells me that H is equal to HF plus XHFG. Apply this equation, okay, and you'll get your X. So HFG, it's HF minus HG, or you can use the direct entry there from the table. Let me give you the direct entry from the table. It is 223.95. Okay, your X is the unknown, you need to find it, and the HF is 3.841. And here we have 111.26, yeah? So what is our X, okay? Use the calculator, you're gonna find our X, okay? Just let me check it. The X is gonna be, okay, yeah, so 111.26 as we found it, or 0.25, depending on the version of your table, okay? There is a slight difference in the refrigeration data from I think the 7th edition and the 8th edition, okay? But it's very slight difference. So if you look at the solution, you'll find it 111 0.25, and with my tables, I guess my tables are from the 7th edition. So yeah, so they are 1.26, okay? But it will not make that much of a difference, yes? So we need to find the quality, and the quality, they got it as, where not they found the quality? Could this question be different? Okay, 1 minute, just 1 minute. Sorry, I had some noises. Let me continue again. Where we were to find the H. Okay, 1 minute. Yeah, we were to find the X. Sorry. Why is not it coming? Why isn't it coming? Okay, so now I need to open this, then go here. Yes, okay. Yeah, so that's fine. I think they got it 0.4 something. Okay, so 1.26 equal to 3.841 plus x multiplied by 223.95. So it should be equal to 0.479. So you can say 0.48. Okay, you can say it is 0.48 in this scenario. Okay, let me go back. Yeah, it is approximately 0.48. Yes. So now what we need to find is the second thing, okay, is the refrigeration load. Okay, so we need now to find the refrigeration load. And what is the refrigeration load? Basically, it is QL dot. Okay, if you don't have the M dot, then you should find QL small. Okay, so now we should calculate the Q capital, or the total refrigeration load, because I guess we have the mass flow rate of the refrigerant. So where is the mass flow rate of the refrigerant? Mass flow rate of the refrigerant. Okay, it's not given, but can you figure out how we can find it? Yes, we know the inlet condition of the water, and we know the outlet condition of the water. We know the inlet here, we know the outlet here. Make mass balance in the condenser, and after you make the mass balance in the condenser, then you are going to find what is the mass flow rate of the refrigerant. Okay, you're going to find the mass flow rate of the refrigerant when you make mass balance between the condenser. Okay, so the flow of the refrigerant inside the condenser and the cooling water. Okay, because the condenser is basically a heat exchanger. Okay, but that its purpose is to reject the heat. Okay, reject the heat from the refrigeration cycle. Okay, but it is a heat exchanger, yani, basically, and then it takes the heat and it rejects it to the water in the cycle. Okay, so yeah, we need to do the heat exchanging. Okay, so first, before we find QL, we need to find the mass flow rate. Okay, you understood why we need to find the mass flow rate, because it is m dot multiplied by QL. Okay, that's what we need to do basically. So first we need to find m dot, and now m dot, okay, H2 or H2 minus H3. So the inlet at the condenser and the outlet at the condenser should be equal to m dot Cp delta T. Okay, so here we have the temperature difference of the water, here we have the Cp of the water, and here we have m dot of the water. What is m dot of the water? It is 0.25. Cp of the water is a constant value, which is 4.184 or 4.14 something. Okay, and we have the temperature difference of the water, which is 26 minus 18. That will gives us 8. Yeah, 26 minus 18, it is 8. So 8 degrees, and here we need to find what is H2, what is H3, and here m dot of the refrigerant. Let me call it refrigerant so I don't forget it. Let me just substitute the values of H2 and H3. H3, we found it before. It was 1.26. So here we put 1.26 minus, what is H2? We have the temperature, we have the pressure of the condenser, which is 1.2 megapascals. So let us find it. H1 is equal to, go to the pressure, 1200. And I can see that the saturation temperature is 46, yeah? And what is our temperature? Remember, it is 65. So this is clearly superheated case. Go to table A13. Now from table A13, you will find that, okay, this is what you will see in the tables when I went there. So you find here 1000 or 100, this is kilopascals. And you see here, this is T saturation, okay, saturation temperature, which is 64 point something, okay. So now you fix the pressure, which is your pressure. Now check this compared with the temperature that you have, which is 65. So since it's clearly larger, then this is superheated, okay. Don't forget this. This is basic knowledge. You need every time when you are solving cycle questions to do these checks, okay. I'm just doing that to refresh you, okay. And table A13 will give us the properties for superheated refrigerant. So I am going to 1.2. Yeah, I have 1.2, luckily. And 65, I don't have a direct entry for 65, but I can do a normal interpolation between 60 and 70, okay? So to do an interpolation between 60 and 70, what I will do is 227.21, because it's exactly at the center, okay? If you go to the tables, 60 and 70, okay? So 65 should be here exactly at the center, okay? So take this value of H, take this value of H, add them and divide them by 2 to get the average, which is going to be H here. But this trick only works if the temperature is at the center point, okay? Between those two temperatures that are given in the table. Okay, so I put 2, or how much is the H at 70? Okay, H at 70, it is 300.61 plus 289.64 divided by 2. So this is my H1, which is 295.125 kilojoules per kilograms. I substitute it here. Okay, and now I find my mass flow rate of the refrigerant, which is clearly 0.184. Okay, I'm not sure of the CP of the water, but it is a constant. It will be given definitely. And 125 minus 111.26. And now we have the mass flow rate of the refrigerant, which is 0.0455, okay, kilogram per second. Usually, sometimes the question asks you to find the mass flow rate of the refrigerant in other units or in different units. So it might tell you like find it in ton per days, okay. So how can you do that? You know that the kilograms, okay, it is or the ton is 1,000 kilograms. So you multiply by here. Here you have ton, and here you have kilograms. So 1,000 kilograms for each ton. Okay, and as I said, ton per days. So you have how many seconds in a day? Okay, first we have minutes, okay, or seconds here up, and here minutes and 60, and then again. So because we want to convert minutes, so 60 again to hours, and then multiply again 24, okay, hours for each day. Okay, this is not our question, but I remember we had something like that before. Okay, because usually the mass flow rate of the refrigerant is going to be a small number. So just like for to visualize this number more, or to we're not that interested in knowing the amount of the refrigerant that passes each second, but rather the amount of the refrigerant that we need each day. Okay, for our cycle to operate. Okay, so it is more convenient, or a more convenient unit to use. Okay, but that if the question asks you to do it. Okay, so just remember, you only need to do like these conversion factors. Okay, put everything, cancel out the canceled units. Okay, so here kilogram will be canceled with kilogram, and here minutes will be canceled with minutes, and seconds with seconds here, and hours with hours here, and you are gonna end up with ton over days. Okay, but that's if the question asks you to do. Now, what is the last thing? Okay, let me see. Now we need to find, yeah, I didn't find the refrigeration load. Okay, so this is a good thing. We found the mass flow rate of the refrigerant, but we didn't find the refrigeration load, which is QL. So it is H1 minus H4. Okay, did we find H1? No, I don't think so. So what is the temperature at 1? It is minus 34. Okay, and again, go check the pressure of 60. Oh, okay, go check the pressure of 60, which is, what is the pressure of 60? Okay, what is this point that we found? Was this H1? Okay, this was H2, not H1. Okay, so this was H2. Yeah, good. H1, okay, for H1, we have a temperature of 35. It's not 35, it's minus 34 degrees Celsius. And we have the pressure of 60 kilopascals. Okay, so go to the 60 kilopascals. Okay, and now when we met 60 kilopascals, we see that the saturation temperature is minus 36.95. So clearly, because this one is higher, so it is gonna be superheated. Okay, because the temperature is higher than Tsat at that value of pressure. So now go to the superheated tables. Okay, and then from the superheated tables, okay, from the superheated tables, we need to go. Okay, 1 minute. It's okay. Oh, so we have the superheated tables. I'm going to, of the refrigerant, I'm going to 60 kilopascals, which is 0.06. Okay, do we have an entry for that? Yes, it is the first entry. And the H that I'm seeking, or the temperature that I'm seeking, is 34, or minus 34. Okay, so I don't have minus 34. In fact, what is there in the tables, it is something like this. Okay, so you need to do interpolation definitely. You have here saturation temperature, which is minus 36.95 degrees Celsius, and then directly under you have minus 20. Okay, so you need to do interpolation here in between to find what is the enthalpy. I believe that the enthalpy here is 227.79, and then the enthalpy here is 240.76. Okay, so when you do the interpolation, you're going to find a value that is very close to here, maybe 230. Okay, let me check it. So what is H1, H1, H1? Yeah, it is 230.04. Oh, not here. Yeah, 230.04 kilojoules per kilograms. Okay, that is our enthalpy of 0.1. Okay, and we found the enthalpy at 0.2. We found the enthalpy 0.3 before, and the enthalpy of 0.3 and 0.4 is the same. So now we are ready to find the refrigeration load. Okay, you can find now the refrigeration load very easily. Okay, let me go and give you, okay, or let me do it now. So Q dot L is equal to M dot, which is 0. What? 0.0455 multiplied by the difference in the H's, which is 230.01 minus 111.26. Okay, so now QL is 0.0455 multiplied by 230.01 minus 111.26. So it is 5.4 kilowatts. This is my refrigeration load. Now I need to find the COP of the refrigerator. What is the COP of this refrigerator? Okay, so the COP of the refrigerator is equal to QL dot over the amount of the work in. Okay, so this is the COP of the refrigerator. Or you can do it in another way. You can say that I want to put it as Q dot L here, okay, and here it is Q dot H minus Q dot L. You can do it in many ways, okay, but this is clearly now, for now, it's the easiest way. And now we have the Q dot L, okay, which is 5.4 kilowatts. And now what we need to find is what is the work inlet, okay? What is the work inlet to this cycle, okay? Now, typically work inlet to the cycle will be the mass flow rate multiplied by H2 minus H1, okay? Multiplied by H2 minus H1. But the question tells me, remember that 450 at the beginning in the question, 450, let me remind you with this here, this 450, yeah, tells me that this 450 is an amount of heat that was gained in the compressor. So I just want to find the work. I'm not really caring about this amount of heat that was added to the compressor. And you remember that the compressor is an open flow device. Yes, the compressor is an open flow device. Here I have the inlet and here I have the outlet of the compressor. Okay, and it tells me like there is an amount of heat gain of 450 watts. Okay, the net heat gain to the compressor. So this is Qn to the compressor, and mainly this term should not be there. Okay, this 450. Okay, this is not QH. Okay, this is just an amount of heat that was gained to the compressor. So mainly, or in an ideal cycle, this amount of heat should not be there or should not be accounted for. But now in this questions, he wants me to consider this amount, and he gave it to me, and I want to know what is the work into the compressor. Okay, so remember, this is not going to be a case of H2 minus H1 multiplied by m dot. No, you have to also consider this amount of heat because the question clearly tells that. And I will just do the first law of thermodynamics on the compressor, which is going to be m dot, okay, H1, this is the inlet, plus Qn, and then plus the work in, and then it's going to be equal to m dot H2, which is the outlet. I know what is the mass flow rate of my refrigerator. I know what is H1. I know what is H2. I know what is this amount of heat. So I should put it 0.45 because I'm always dealing with kilowatts. Here I have kilowatts. Here I have kilowatts. And I need to find the amount of work in kilowatts, in fact. Okay. So let's find it quickly by the calculator. We had the refrigeration 0.0455 multiplied by where is H inlet, which is H1. And H1 we found it before, which was this value, so 230.04, and then plus the 0.45, the heat, and then plus X, which is unknown, equal to 0.0455. Okay, I hope that you're following. Okay, I'm just doing it quickly because now the rest is easy, you know, so we find everything. Now it's just application using your calculator. Okay, but I just want to do it here in front of you so you get used to it. Okay, and then lastly we have the H2, so we'll go back now to H2. Where is H2? Where did we find it? Yeah, here is H2. So 295.125. Okay, so shift solve equal. Now we have our work into the cycle equal to 2.51. Okay, kilowatts. Now our COP is equal to 5.4. Yeah, that's what we found before. And here 2.51. So it is approximately 2. Yeah, our COP is approximately 2, I guess. 2.15. Yes, this is the COP. And the last thing is, if let's imagine that the theoretical, or not, let's imagine, what is the theoretical maximum refrigeration load for the same power input to the compressor? So use this exact same power input, okay, with that heat addition or heat gain here, okay, and give me the QL. So this means that the theoretical value, which is like the maximum value that I can get, so I have to calculate COP of a Carnot, okay, so of a Carnot cycle, which is going to be equal to, what is the COP of a Carnot cycle? Is 1 over 1 minus TL over TH. Yes, this is COP of a Carnot cycle. And here I have 1, I have here 1 minus, and here is the temperature of the height or the load of the it's the temperature of the low or the lower temperature in the cycle, which is the temperature of the where we are extracting, or the temperature of or from we are extracting the heat, and here is the temperature for which we are rejecting the heat. Okay, so this is the temperature of the extraction, and this is the temperature of the rejection. Okay, if you go to your cycle, okay, so you can see clearly that the temperature, okay, so the temperature of where you are extracting that heat is minus 30 degrees Celsius. Okay, if you go to your cycle, the temperature is minus 30 degrees, and the temperature of the rejection is 18 degrees. Okay, which is the water that we are rejecting to. Okay, so let me go back here and show it to you. So here, okay, yeah, let me delete. You can see that is used to keep the refrigerated space at minus 30. Okay, if you wondered why we didn't use this information in the calculation, that's because it is not a point here in the cycle. It is the maintained or the required refrigeration space, okay, or the refrigerated space temperature. So this is a refrigeration cycle. Okay, let's imagine that this is a refrigeration cycle, and it works here to cool your refrigerator. Okay, so we need to maintain your refrigerator at minus 30 degrees Celsius. Okay, and the cycle is working to provide you that. Okay, so here you have the compressor of your refrigerator. Back there you have, okay, in the back you have the rejection coils, which are the which are the condenser coils. Okay, and you have the evaporator coils basically in. Okay, the evaporator coils, and you have the throttle valve, okay, or the expansion valve. Yeah, so I need to maintain my refrigerator at minus 30 degrees Celsius, and I am rejecting the heat from the evaporator coils, okay, to a water, and that water have a temperature of 26. So what is the temperature that the water is entering with? Yeah, the water is entering at a temperature of minus 18. Okay, so I'm rejecting to a water that have a temperature of 18 degrees Celsius, and now the water temperature will rise to 26 degrees Celsius because of that amount of heat that I am rejecting to the water. Okay, so this is the heat QH, okay, the amount of heat rejection to the water, and then the water temperature will increase as a result of that heat rejection. Yes, did I write this equation correct? I'm not that sure. Let me make sure that it is correct. What is the COP of a Carnot cycle? What is the COP of a Carnot cycle? COP. I'm not that sure of the equation. Forgot it actually. Sorry for that. Let me review it from here. Maybe I can find it. So this is a refrigeration cycle. Yes, I found it. For a refrigerator, okay, yeah, it is not correct. Okay, so for a refrigerator, the one that I wrote is for heat pump. For a Carnot heat pump. I'm doing a Carnot refrigerator. So this is for the Carnot refrigerator. Okay, so equal to 1 over what we said, that is the temperature of the rejection. It is 18 plus 273. Don't forget to convert to kelvins. Whenever you have ratios, including temperatures, always convert to Kelvin. You have multiplication, anything, any process, except if you have subtraction, then the difference will be the same. So you don't need to convert if you have subtraction. But for multiplication, addition, anything else, ratios, you have to add the 273. What else I have? 18 plus 273, and down there is the temperature of the extraction, or the maintained temperature of my space. Okay, minus 1. I'm now going to find the COP, and remember that for a Carnot COP, this Carnot COP is going to be definitely higher than the normal COP, okay, of our normal cycle. So of course this COP is going to give me, okay, oh no, it's not correct. What did I did wrong in the equation? TH 1 over, okay, here minus 1. I did plus 1. My bad, yeah. So here is minus. Okay, so it is 5.06, okay, which is, yeah, definitely higher than this by, and now he wants the Q okay, L, the theoretical one. Okay, so that's the maximum QL that I can extract from my space. Okay, so it is equal to 5.06, and he told me for the same amount of work. Okay, so multiply by work n. Remember that the COP, okay, the COP is equal to Q dot H over the work n. So the Q dot H is going to be equal to the COP multiplied by the work n. And he told me for the same amount of the work n, as we talked before, so 2.51, and now it is going to be, look, 12.7, okay, kilowatts. So huge difference between 12.7 kilowatts and the 5.4, the actual one. Okay, so this is just a question and therefore comparison for you, like, to understand or realize how much we are or that is wasted from us. Okay, because we cannot reach the maximum amount. Of course, it's the one for the Carnot. Okay, so yeah. Okay, so that's why we use vapor compression cycles, because the vapor compression cycle is a more realistic, okay, more realistic representation for refrigeration cycles. Okay, so this one is the ideal refrigeration cycle, not the Carnot. Okay, the Carnot is not a realistic representation for the refrigeration cycle. Okay, the vapor compression is the realistic. Okay, so we need, in fact, we need to target this performance of the ideal vapor compression cycle. Okay, so even though this one maybe we will not be able to reach it because we have some isentropic efficiency of the compressor and some isentropic efficiency basically in the compressor. Okay, so yes, you see how easy it is. It's just like how you used to do the normal Carnot cycle. Okay, not the Carnot cycle, how you used to do the Rankine cycle, but now you have less device. Okay, less devices. So you have compressor. Okay, and here you have throttling valve. H is constant. Then your work is done here. Okay, I just took some time. Okay, because this is the first refrigeration cycle question we solve. But definitely now in the second one we'll go a bit faster. Okay, so now in the second question, we have a modification of this refrigeration cycle. Okay, so remember this is question, if you want to go back to the questions, this question is 11, 18. Okay, let me delete all this. Okay, can't I enlarge this? Okay, I want to delete. Okay, delete. Is my mic on? I'm gonna cry if it is not on. My mic. Okay. Yeah, it is on. Pardon me. Okay. Okay, lots of things we did in this question. Okay, now the cascaded cycle, while I'm deleting, the cascaded cycle is just two vapor compression cycles on top of each other. That's it. That's basically it. Like nothing more, nothing less. Two vapor compression cycles on top of each other. You have now a third pressure in the cycle, which is called the intermediate pressure. Okay, and sometimes this intermediate pressure can be the same. Okay, for the upper cycle and for the lower cycle. So that intermediate pressure is going to be the same sometimes, and sometimes it's not the same. Okay, so maybe the pressure for the lower cycle is higher and for the upper cycle is lower, or maybe the other way around. So it's not always because we have the upper cycle, our pressure will be higher there in the upper cycle. Let me show you how it goes in a graph. Okay, I don't think we will reach even here, but if we reach, we will delete at that time. Okay, so we have two vapor compression cycles on top of each other. I have here my throttling device. I have here my evaporator. Okay, I have here my compressor. Okay, and then I have here again my condenser. Okay, and then here, okay, here. Now the evaporator of the upper cycle and the condenser of the lower cycle are connected in a one heat exchanger. Okay, so this heat exchanger includes both. Uh, how does it work? Like I have here one fluid, okay, that is inside the condenser, and we know that from the condenser we have rejection of heat, and in the evaporator we have extraction of heat. So this heat is directly extracted in the evaporator that is on top of it. Okay, so condenser rejects, evaporator extracts and takes. Okay, so that's how those two devices are working together here in the same uh, uh, for the two cycles, okay, the lower one and the upper one. And then again a same or a typical vapor compression cycle. Here I have an evaporator, and here I have the second compressor. Okay, second compressor, and here back again. Okay, so we have here the pressure of the evaporator. This is the lower pressure, and this is the upper pressure, which is the pressure of that condenser. And now this is the intermediate pressure. So this intermediate pressure sometimes can be common. Okay, so the fluid in this cycle here, the lower fluid or the lower part here. Okay, let me call the points. This point 1, this point 2, this point 3, this point 4. Okay, and now this is point 0.34. Okay, so this point 5, this point 6, this point 7, this point 8. So between 0.5 and 8 and between 0.2 and 3, sometimes they can work all on the same pressure. So this intermediate pressure is the same. And sometimes this stream have the high pressure. Okay, so I have here first intermediate pressure, second intermediate pressure. Okay, so I have 4 pressures in the cycle. And sometimes this pressure can be higher. Okay, so it's not that because it goes here in a coil that is lower, then it's gonna be higher. Don't be fooled by the drawing. Okay, so the drawing like have no meaning. I have the pressure here maybe in the evaporator, and now this is the condenser. So as this question, okay, as you'll see in this question, I have this one is 0.5 megapascals, and I have this one as 0.4 megapascals. Okay, so don't be fooled by the drawing. Okay, this is one of your homework questions. Don't be fooled by the drawing. Okay, the lower temperature, okay, or the pressure of the the pressure of the condenser of the lower cycle can be higher than the pressure of the evaporator of the upper cycle, okay, which is now 0.4 megapascals. Here we have 0.5, and sometimes they can be common, and sometimes this one is going to be higher. Okay, so pay attention to the question as it tells you. And we have pressure limits. Okay, so this is the farthest higher pressure and the farthest lower pressure. So this is 1.4 megapascals, and here we have 160 kilopascals. Okay, we will solve those cycles together. Heat rejection from the lower cycle to the upper cycle takes place in an adiabatic counterflow heat exchanger. He tells me this information. Okay, I should know it. And then the lower, look, the upper and the lower cycles are 0.4, 0.5 respectively. So the upper takes 0.4, the lower takes 0.5 respectively. In both cycles, the refrigerant is a saturated liquid. Okay, in the condenser. Okay, so exit and saturated vapor in the compressor. So he tells me an information that will make my life easier. So here and here, he tells me this point is saturated liquid always, and this point is saturated vapor always. So the inlet and the outlet of the evaporator all work inside the dome. Starting from here, I'm ending here. Saturated vapor, saturated liquid. That's what's happening inside both condensers. Okay, inside both condensers or both evaporators. Let me write correctly. And then the state of the compressor. Okay, and the compressor is estimated. No, not here. Okay, so in both cycles, the refrigerant is a saturated liquid at the condenser exit and a saturated vapor at the compressor inlet. Okay, so not from here to here. Okay, I did something wrong. It is from here, okay, here, and here. He tells me that those 2 points are saturated liquids, So outlet of the condenser is always a saturated liquid, and inlet of the compressor is always a saturated vapor. So this is what he says: saturated liquid at the condenser exit, condenser exit, saturated liquid, saturated vapor at the compressor inlet, saturated vapor. And yes, and the isentropic efficiency of the compressor is 80%. Okay, so again, we have also an isentropic efficiency of both these compressors. If the mass flow rate of the refrigerant through the lower cycle, okay, so here I'll put m dot in this cycle. Okay, so m dot 1 I will call it, which is 0.11 kilograms per second, or let me be consistent with the terminology in the book, so call it m dot a, and this is m dot b, which is equal to he wants me to find it actually, yeah. So this is one of the things that I need to find. So I need to find the mass flow rate of the refrigerant through the upper cycle, the rate of heat removal from the refrigerated space. Okay, so the rate of the here, this is the refrigerated space. I'm removing heat from it. Why not this one? Because this one is not removing the heat from the refrigerated space. It's removing the heat from this cycle. Okay, so those two cycles are like coming in one package. Okay, the refrigerator will be placed here. Okay, here is the refrigerator or the refrigerated space and maintain that temperature, not here. Okay, so those two cycles, what is happening that if we only operate by one cycle, then this heat will be rejected. It tells you no, put another cycle that the heat will be rejected to that cycle, and then after that the heat will be rejected. This will increase the COP of the cycle. Okay, so that's a complete cycle, but it's consisted of two parts. Okay, and here is the amount of the heat extracted. Okay, QL. I wrote QH. And here's the amount of the heat rejected. So that's the QH. Okay, what he wants the mass flow rate of the heat removal, the mass flow rate of the refrigeration through the upper cycle, the mass, the rate, why I'm reading the mass, the rate of the heat removal from the refrigerated space, which is QL, and the COP of this refrigerator. So let's start, okay? Point one, quickly. Point one is saturated liquid, okay? Saturated vapor at that pressure at 160 kilopascals. Okay, so H1, I can find H1 directly. What are the H's I can find directly? Okay, so it is Hg, okay, at a pressure of 160 kilopascals. Okay, so this one I can find directly. And also H5 I can find directly, which is Hg at a pressure of, okay, remember the upper pressure, don't be fooled, it is 0.4 megapascals. Okay, and what I have also, I have here and here, so H3 and H7 I can get them. H3 is equal to Hf at a pressure of, okay, what is 0.3? The pressure of 0.3 is 0.5 at a pressure of 0.5 megapascals, and H7 is equal to Hf at a pressure of the higher farthest upper pressure, which is 1.4 megapascals. Okay, 1.4 megapascals equal to, now I rearranged everything. I can find whatever I want in this, okay, in this from these edges. Okay, so I'll find this, and then what else I need? Okay, so this edge is gonna be coming from here, and this edge is coming from here. But first I have to find the isentropics ones, okay, then before finding the actual ones. Okay, so H2, okay, and H6, okay. First I need to find the isentropic ones before using the compressor. So how I'm gonna find the isentropic ones? The isentropic ones will be found if we put the entropy constant. Yeah, if we put the entropy constant, okay, and use that same pressures. Okay, so pressure of 0.2 I know, pressure of 0.6 I know. Use those pressures with the entropy. Okay, so these are gonna be found from the fact that S6 is equal to S, what is the 0.5? Okay, and here we have S2 equal to S1. Not always, it's just for the isentropic one, then I'm going to find the actual one. And then pressure at 2 is equal to 0.5 megapascals. Pressure at 6 is lower, okay, 0.4 megapascals. Okay, yeah. So here I'm going to find, so I need just S and S6 and S5, okay, S1 and S5. I will find them also from here, okay, because I have everything. Then after that, I will apply that. I have an isentropic efficiency of the compressor, which is equal to 80%. And I'm going to work with that to find what are the H2 actual and what is the H6 actual. Okay, so let's go in it step by step. Don't rush it. We need first the quality of, I'm keeping reading that question. Okay, we need first the mass flow rate of the refrigerant through the upper cycle. So I need to work with this point and this point. okay, and here make a mass balance between here and here because this is a heat exchanger. But again, 0.2 and 0.4 are not there. Sorry, 0.5 is there, but 0.2 is not there. So first find the actual 0.2 and then work with the cycle. Okay, find first the actual 0.2 and then work with the cycle. Or let me tell you something. You need to work all the cycle to find these, okay? Because you don't have 8, and then you need to go work with H7. Now H8 is gonna be H7. Okay. Okay, this one is found. 3. Okay, we can found it. Yes. 5, okay, yeah, it can be found because it is saturated vapor. Now I need to find first 0.2. Okay, so let me first get the actual of 0.2 before going and calculating the mass flow rate of the upper cycle. Okay, because I need this H, this H, this H, this H. Okay, let me report those quickly. Okay, so going to the tables quickly, very quickly. Go 160 kilopascals. What is the HG? HG is 24. Okay. Hope I don't rush it and get wrong numbers. 2, 4. Oh, we're beginning to get wrong numbers from now. 241.11. Okay, I'm not gonna write the units. Okay, but this is not a good practice to not write the units. You should always write your units. Okay, and then Hg at 0.4 megapascals, which is 4,000. Not 4,000, 400 kilopascals. So go to 400 kilopascals. And get what's the SG there. So for 400, okay, I was at 160. At 160, I got what is 241.11. So for 400, I'm getting 255.55. So 255.55. Okay, and here for 3, okay, I should work with 500. Okay, so 500, I'm going to it, and now I will find HF, not HG. Okay, so not HG now HF. So this one is 73.33, and this one with the 1.4 or with the 1,400. So what is the HF? I can see that is 127.22. So 127.22. Okay. Now, of course, after knowing those 2 points, this one is equal to H4 because I have a throttle. And this one is equal to H8 because I have a throttle. Remember, this is a throttle working from 7 to 8, so constant enthalpy. Like this is the beauty of the expansion valve. Constant enthalpy directly, and then no need to do anything else. What else we needed? Okay, yeah. So after I found those, I need to get what is S1 and S5. Okay. So what is S1? And what is S5? Okay, same thing. I'm going to get HG, SG at that pressure, and now SG at that pressure also. Same thing. Nothing will change. But I just want to calculate the entropy. So 160. What is the entropy at that? 160. So what is SG? Okay, 0.4. No. At 160, the SG is 0.94190. So 0.94190. Okay, and for S5, which is at 0.4, which is 400 kilopascals, so I have 0.92691. So 0.92691. Okay, take those two values, plug them there. Okay, here, and then using this entropy and this pressure, okay, calculate what are the S2S and H6S. Okay, so I'm going to check with my first entropy, which is 0.9414, and my pressure, which is 500. So go to 500 and check this value of entropy, which was, remember, 0.941. So with 0.941, I'm having a superheated case because my SG is 0.92, not 94. So I go to table of the superheated tables, and then I go to 500. Okay, to 500 megapascals. Sorry, 500 kilopascals because they are 0.5. Okay, and then I don't. Oh yeah, I have a direct entry for 0.5. And what is my entropy? Check 0.24. I have okay, it's not 0.24, it's not 0.938, it's not 0.97, so it's clearly between 0.383. and 0.9703. Okay, it's gonna be more closer to 0.383. So we'll find that the enthalpy is somewhere like 265, something like that. Okay, let me just check the value. Okay, so to be more quick, so this is question 58, I guess. Yeah, this is question 58, and it's also one of your homework questions. Okay, so I just need to get H2 actual. What is H2 actual, please? H2 actual. H2. Yeah, as I told you, it is going to be between 200 and 200. What is it? Yeah, we said that it's going to be between 263 and 273. So I said like it's going to be around 265. Okay, and I see here that the solution manual is getting it 264.55. Okay, so it doesn't matter actually. I'm just gonna use their values now for simplicity. Okay, so 264.55. Okay, whatever. And here H6 again, same thing. Make the entropy constant, which is 0.92. 6, and then go with 400 kilopascals. So with 400 kilopascals, I can see that it is 0.926. Okay, and I have here 0.9269. Oh, what is this? I need to make it constant with which entropy? With this entropy. Okay, yeah, so this entropy is at 0.4. Yeah, okay, this is what I missed. This pressure should be 1.4. Okay, this pressure should be 1.4. So be careful. 1,400, because that's the upper pressure, the uppermost pressure. So 0.91, that's where the Hg is equal to 0.91. Okay, which is clearly less than my H. Okay, sorry, this is the Sg, which is clearly less than my S, so it is superheated. And now I'm going again to the superheated tables, but now for different pressure, which is 1.2. Now I'm searching for 0.92. I can't find the 0.92, which is actually at 278.27. Okay, so it's going to be around that value, 278.27. Okay, 0.27. Okay, but it will be different in the digits. Okay, or in the decimals. Okay, so what is H6 actual? Yes, it is 281.56. Okay, so fairly close, 281.56. Okay, yeah, fairly close. Okay, maybe also it is some small errors coming from the different versions of the tables that I told you. Okay, but now you have everything. Okay, now how to implement this isentropic efficiency? You say that the isentropic efficiency for a compressor, because it's a work-consuming device, it is going to be H, okay, for the first compressor and for the second compressor as well. But now I'm more interested with the first compressor because I want to find first H2 actual. Okay, so here H2 actual minus H1 over H2 isentropic minus H1. Okay, and before we put isentropic or actual, okay, just to make sure. Okay, now this is a work consuming device. So the isentropic work that I will be consuming should be less than the work that is being consumed. Because when we have an isentropic process, then we either minimize the work that is input or we maximize the output work. Okay, and because this is a work consuming device, so we are minimizing the isentropic. And remember, the efficiency should be less always than 1. So isentropic above, okay, because this is the minimum and this is the maximum. Okay, and here also same thing, but now for different values. So H6S over H6A minus H5. Okay, that's gonna be it. We're gonna find what is H6A, what is H2A, okay, and then proceed with them. So H2A and H6A. Okay, you know how we got all the values, H1 and H1 and H5 and H5. They're both saturated vapors. Okay, saturated vapor. So we know the values: 241.11, 255.55. Okay, so 241.11, 241.11. Yes, and 255.55. Okay, so 241.11 and 255.55, 255.55. Okay, I know what is the H's. Okay, so H2 isentropic and H6 isentropic, so it is 264.55, so 264.65, and here we have 281.65. Okay, then find, yeah, you just find your H2A and H6A. Okay, clear? After you find your H2A and H6A, what you are going to do, we're going to say I'm going to do mass balance to find what is the mass flow rate of the upper cycle. Okay, now we are beginning to solve the question. Mass flow rate of the upper cycle, okay, multiplied by what is the flow that is passing the upper. Okay, remember that you have here a combination of an evaporator, okay, working with a condenser. Okay, and here we have a fluid, and here we have a fluid, and this fluid for the upper cycle. So here this is m dot b, and we need to find this is m dot a that we already have. This is 0.1, this is 0.4, this is 0.5, this is 0.6, and it is actually in a parallel flow manner. Okay, it is working in a parallel flow manner. So the flow is going in these directions. Yeah, what else, or not what else, what should we do? So m dot b, h5 minus h6, okay, h6, which is equal to h what? This is 5, oh, this is not 6, this is 8. So h8, which is equal to h7, because here we have throttling, okay, from 7 to 8, and equal to m dot a, which we know, multiplied by h what? H1. Yes, this is not 1. I'm messing up it again. So this is 2. This is 0.2, and it's not in a counter. I was confused why it was in a parallel flow manner. It should be in a counter flow manner, actually. Yeah. So this is 3. Okay, so H3 minus H2, or H2 minus 3, because 2 is higher. It doesn't actually matter. And then I have this. Of course, you should use the actual H2A, actual H2A always. And these do not have actual anisotropic, the rest of them. So just find this. Okay, what is it? What is m dot b? Okay, and after you find m dot b, what does he need from you? He needs you to calculate the rate of heat removal from the refrigerated space. So what is the rate of heat removal from the refrigerated space? M dot A, because the removal is from down, okay, from here, from this evaporator. Okay, so rate of heat removal from this evaporator, here we have 0.1, here we have 0.4, so it is H1 minus H4. This is the rate of the heat removal from the refrigerated space. And also, what does he need? The COP of this refrigerator. So I can calculate the work in, but I have to do that for both pumps. Or what else I can do? If I don't want to do that for both pumps, I can find what is QH, okay, and this will save me. Okay, so this is QL, Q dot L, and what is Q dot H? Q dot H is equal to, use that fact that you got M dot B, and use H6 minus H7, okay, to get Q dot H, and then COP. Okay, now in this case, using Q dot H and Q dot L will be easier. So Q dot L over Q dot H minus Q dot L. Okay, that's our end goal, to calculate the COP of this refrigeration cycle. Okay. Yeah, I know it is a bit long, or not a bit long, but you feel like there are so many steps, but if you were doing it in a paper with yourself, you will see like it's really nothing. You are solving the cycle much faster than if you are solving a Rankine reheat cycle. Okay, believe me, like you don't have any processes to do from 7 to 8 and from 3 to 4, and then that's directly the throttling device or the expansion valve. And yeah, so it is much quicker. Okay, the only thing that maybe slowed us a bit was the efficiency of the compressor, but it was fine. It was the same thing for both compressors, so don't forget to apply it. Okay, and yes, now after we find QL, we can find QH and then do the equation. Or if you don't mind, using the two or calculating the two what we call them, calculating the two pumps, two compressor powers. Okay, so because we have here an upper compressor and a lower compressor. Okay, so here a lower compressor, okay, and an upper compressor. So you need to find what is work dot in. What is work dot in? Not call me 1 and 2. We call them A and B. Okay, so you need to add them together to find what is the total inlet work. Okay, now let's do the final modification of these innovative cycles, which is called the not the cascaded. This one is the multi-stage refrigeration cycle. Okay, so multi-stage refrigeration cycle. What does the multi-stage refrigeration cycle does? Okay, so if you remember from your theory, the multi-stage refrigeration cycle, multi-stage refrigeration cycle will not have two cycles that are working back to back with each other, but rather it will insert a flash chamber inside the cycle, and the flow rate will be some of the flow rate, okay, that is exiting, okay, the throttling device will go to this flash chamber, okay, to a pass, okay, that we take from that flash chamber, okay, directly to the compressor, okay, to the upper compressor, and the other rest is going to recirculate the lower part of the cycle. What do I mean exactly? Let me show it to you in a rough sketch. Okay, so yeah, we have our condenser, okay, and evaporator. You understand these things, and here we have our compressor, okay, compressor, and here we have our throttling device or expansion valve. No, this delete. So yeah, something like this, okay. So yeah, this is your typical vapor compression cycle. What happens here is that we take some of the extract of from the throttling device, okay, here to a device that we call the flash chamber. Okay, and the flash chamber is like just a mixing chamber, okay, or the flash chamber. Flash chamber. And it's going to divide the flow. Some of it will go here, some of it will go down and recirculate inside the evaporator. Okay, now this one that is going in that way, okay, of course I have two pumps in this cycle, okay, compressors in this cycle. I forgot. Okay, so we have here a compressor, okay, and there we have another compressor, okay, because the pressure difference is going to be high. We need two compressors to accomplish the task. Okay, and now this extract is going where? It's going directly after that compressor, okay, here again to another mixing chamber, okay, and these flows are going to be mixed. So where in the cycle do we have complete flow rate or total flow rate of the cycle? Here I have total flow rate, okay. The ones with the total flow rate, I'm going to mark them in green. So here I have total flow rate of the cycle, here I have total flow rate of the cycle, here I have total flow rate of the cycle, here I have, okay, all of this total flow rate of the cycle, and also till here it is the total flow rate of the cycle. Now we have our division, okay, some will go there and some will just do recirculation. Okay, I put it in a different color. What is the flow? Okay, let me choose this color, purple. Okay, so and some is going to be recirculated here. So how can we find the amount that is? So let us call that one the total one. Let's call it m dot. Okay, this is the m dot of the cycle. And these two extracts, okay, always they're going to be the same. Okay, so if you want to memorize this information, memorize it. Okay, this is going to be x6, and this is going to be 1 minus x6 of that flow rate. Okay, so this is 1 minus x6 multiplied by m dot. Okay, and this is x6 multiplied by m dot. Why is that? Because let us do the TS diagram of the cycle, okay, to follow it closely, or not. Let's not do that completely. Okay, I'm going to put the process after the after the throttling device. Okay, so I have there a point. Okay, and after the throttling device, I have this is the new point. Okay, so here from this point, I will have the division. Some of it will go directly to the compressor, which is going in this way, and some is going to recirculate back. Okay, so the one that's recirculating back, it is this amount. Okay, so this amount is recirculating back. And now I have, this is my dome. Okay, this is actually my dome. Okay, so what is this point? Okay, what is this point? Okay, or what is the x of this point? Okay, so the x of this point is going to be the mass of the vapor over the mass of the total mass. Yeah, so mass of vapor, okay, or the vapor line. Okay, this is the vapor line, and this is the this is called the what do you say? And this is the water line. Okay, so from here to here, that's the vapor. From here to here, that's the water. Okay, over the total one. Okay, so that's gonna be x. Okay, that is x. X is equal to the vapor amount. Okay, over the total amount, which is the one that is going there, the extract that's going there. That's why we say that this amount of flow is x x of this point. Okay, so x6, because we call this point 6, and the amount that's going to be recirculated back is in fact the remainder. So it is 1 minus x6. Okay, it's not 1 minus x6, that's the amount of the flow. This is the percentage of the flow that is divided. Okay, so the flow rate here, okay, the flow rate, okay, of this point, what is the terminology for this point? This is 0.3, and we call that 0.8. Okay, and here we have 0.7, something like that. Okay, so this is m dot 3, okay, is equal to x multiplied by m dot total, and here 1 minus x is multiplied by m dot total. Okay, is gonna be equal to our m dot 7, which is the same as m dot 8, which is the recirculation here. Okay, then again here they are going to combine, and they are going to go as the full flow rate there in the cycle. Okay, so just memorize it. The part that goes to the right is going to be an extract of the flow of a ratio of x6, and the part that's recirculated back is an extract of the flow with a ratio of 1 minus x6. Okay, now after we understood everything in the cycle, let's solve the question. Okay, let me just delete here. Okay, so I'm deleting. Yes, so I will consider a two-stage cascade refrigeration system operating between the pressure limits of 1.2 megapascals and 200 kilopascals. Also here we have also intermediate pressure. You know this, here this, the extraction, it have an intermediate pressure. Okay, so it tells me that it operates between the two pressure limits of 1.2 megapascals. You have to be used to how to interpret or how to convert the words and the numbers into a graph, because he's not going to give you the layout of the cycle. Okay, I don't know, does he allow equation sheets? I guess so. If he allows equation sheets, or if the professor allows equation sheets, then you can do the layout of the cycle. This will help you a lot. And we have refrigerant 134A, of course. The refrigerant leaves the condenser as a saturated liquid and is throttled to a flash chamber operating at 0.45. So this is the operation pressure of the flash chamber process, kilopascals. Oh, sorry, megapascals. And now we have a part of the refrigeration. Okay, evaporates. He just explains the cycle. And the liquid in the flash chamber is throttled. Okay, here I had the information. The refrigerant leaves the condenser as a saturated liquid and is throttled to a flash. So this is the condenser. This point is saturated liquid. Okay. Of course, this point is always going to be a saturated liquid if I don't have information, and this point is going to always be a saturated vapor if I don't have information. Okay. So always the refrigeration cycle. You start from here. Okay. And then you go like that, and then you have something like this. Okay. Okay, and then something like this. Okay, so always if you don't have enough information to tell you, then take the first point as saturated uh, vapor and take this point as saturated liquid if you don't have enough information. Okay, not always, but if you don't have information, just like in Rankine cycle, okay, since we have here the starting and here we have the pump, okay, and then here we have something like that. Yeah, so if you don't have the anything about this point, then you're going to assume that's saturated liquid. Yes. Okay, so the same thing goes for refrigeration cycles if there is no enough information. But now he tells me that, yeah, I want this one saturated liquid. Does he want the compressor inlet to be saturated vapor or no? Let me continue. The mixer is then compressed to a condenser pressure by high pressure compressor. The liquid in the flash chamber is throttled to the evaporator pressure and cools the refrigerator space as it's evaporated in the evaporator. The mass flow rate of the refrigeration through the lower pressure compressor. So where is the lower pressure compressor? This is it. It tells me that the mass flow rate here, okay, so the 1 minus x6 multiplied by m dot total is equal to 0.15. So this is the amount of mass flow rate that is recirculated inside, okay, or for the lower pressure condenser. So I can't find the total m dot if I found x6. And what else? The rate of heat removal from the refrigerator space, which is QL. And if the refrigeration is operated between two single stages between the same pressure limits and the same compressor efficiency, compressor efficiency at the same flow in part A. Okay, so I don't have isentropic efficiency of a compressor. So basically this part, or this last part, tells me that what is the rate of the heat removal, so QL, okay, and COP if this refrigerator is operated on a single stage cycle. Okay, so I don't have I don't have the multi-stage cycle. I have only one stage cycle, which is the normal cycle. And what will be if we are working on the same pressure limits and same temperature limits, what is going to be the differences, okay, in the COP, okay, or what's the difference in the heat removal, the QL. Okay, if we have only one stage cycle. This is question 90 or 59. Okay, and yeah, so that's it. Okay, now let us go there and what should we do? Okay, not from here, from here. Okay, do we have isentropic efficiency of this? Does he say anything? Leaves the condenser saturated, throttle the flash chamber. Okay, leaving condenser. Oh yeah, we have. Assuming refrigerator leaves evaporator as saturated vapor and isentropic efficiency is 80% for both compressors. So the isentropic efficiency of both compressors is 80%. Again, we should do that calculations, okay, to find. But I'm not gonna bother by it a lot. I just want to show you the principle. Okay, when you start solving, what should you do? What is your approach? Let me delete. Okay, sorry, I'm deleting. Okay. Let us put the points, since he didn't specify any points on the graph, let us put the normal points that the cycles work with. Okay, so this is point 1. Typically in this cycle, this is point 2 before the flash jumper and after the low pressure compressor. And after the low pressure compressor, with that is being mixed with the flash chamber. Okay, so we have here point 9. So it is the inlet to the high pressure compressor. And we have here 0.4, which is the inlet to the condenser, 0.5, okay, the saturated liquid, 0.6 after the throttling device, okay. Are we missing a point? Do we talk anything about 0.7? 0.7, where is 0.7? Yeah, I forgot something. There is here also a throttling device, okay, because otherwise we need to throttle, okay, make the throttle in doubles. So this is 0.7 after the flash temper, this is 0.8. Yes, this is the complete cycle. So when we find H or X6, we are going to find the mass flow rate of the refrigerant through the upper cycle. Okay, what is H of this point? Okay, this is the easiest thing that we need to find. What is H of this point? We have the pressure, which is 1.2 megapascals, and we know that it's saturated liquid. So now go and say that H5 is equal to HF at the pressure of 1.2 megapascals. So this is H5. So easy, very easy. Let's go. H5. Okay, H5 with 1200. I have 117.77. Is that correct? Yes, 117.77. Okay, this is my H5. Okay, and now H6 is equal to H5, which is equal to 117.77. What's left for us is to calculate X6. Okay, so now the pressure at 6 is equal to 0.45 megapascals. So check those two conditions and from them get what is your X. I am going to the pressure tables and I'm going to see that 400 or not 400, 450 kilopascals, which is 0.45 megapascals. And with this H, it is of course between. So we have X directly. And what I was going to say is that 60, okay, remember that the X is, what is the X? X is H, okay, minus HF at HFG or over HFG. So our H is 117.77 minus what is HF at that? Did I messed up anything? Yeah, no, I did everything correct. And the HF is 68.81 over HFG, which is 188.71. I get my X. My X is equal to 0.259. This is my X6. Okay, what is the mass flow rate now? What is the mass flow rate of the cycle? As the questions tell me. The mass flow rate of the refrigerant through the high pressure compressor. Through the high pressure compressor, it is the mass flow rate of the total cycle or the total mass flow rate. So I'll tell him that you gave me m dot, okay, multiplied by 1 minus x6, okay, the one on the lower pressure compressor, that's what you gave me. And you told me that that one is the mass flow rate through the low pressure compressor is 0.15, okay? So you told me that this is 0.15. So now I'm gonna substitute my x and I'm telling you that the total mass flow rate is 0.15 over 1 minus x, which is minus 0.259. Okay, that's the only trick in the cycle, okay? And if you write it down in your equation sheet, then it's done. Okay, this flow or this stream is x6 and this stream or this recirculation is 1 minus x6m. So 0.15 over 1 minus 0.259. So I am getting 0.2, okay? And just to make a sanity check, okay, to see if your results make sense, okay, this value should of course be higher than this value because this is only an extract from the total mass flow rate. Okay, and if we want to find what is the mass flow rate here, the one that's going here, okay, either we are going to multiply the total, okay, so the mass flow rate at the chamber, okay, after the chamber, or the extracted amount, it is either going to be x6 multiplied by m dot total, okay, as I told you, or you can say that it is m dot total minus 1 minus x6 multiplied by m dot total, and here we calculated 0.202, and here it is minus 0.15, so it is equal to 0.202 minus 0.15, so it is 0.052 kilograms per second. This is my mass flow rate that's going to or after the flash chamber. Okay, what else he wants me to find? He wants me to find the rate of the heat removal from the refrigerated space. So the rate of the heat removal from the refrigerated space is definitely this one, QL, rate of heat removal from the refrigerated space, not the rate of the heat extracted or the rate of the heat rejected to the environment. No, rate of heat removal. From where? From the space, from your refrigerator. Okay, so what was Q dot L? Okay, Q dot L. Be careful. The flow through the evaporator is not the total flow rate. Okay, so it is 1 minus x6 multiplied by m dot total. Okay, now what h1 here I have, and I have h8, so it is h8 minus h1. Be very careful. Okay, it's h1 minus h8. Doesn't matter with the sign. Okay, you're always gonna put it positive. It's equal to, he gave me what is this amount, which is 0.15, and I need to find h1 and h8. So what is h1? Did he tell me anything about it, about the h1, then the liquid and the, okay, part with the refrigeration, low pressure. The mixture is then compressed to the condenser pressure by the high pressure compressor. Cool that it vaporizes in the mass flow rate of, assuming that the refrigerant leaves the evaporator as saturated and the isotropic conditions. So yeah, it tells me that we need the refrigerant to leave the evaporator as saturated vapor. So he says that clearly that this point is saturated vapor. I told you always, if you are not given it, then it's going to be definitely saturated vapor. And now the saturated vapor is at which pressure? At the lower pressure of the cycle, which is 200 kilopascals. So H1 is equal to Hg, okay, at 200 kilopascals. And what else I need? Okay, and I need H8. Yeah, I need H8. H8 can be directly taken from H7. Okay, so I can take from H7 and go to know what is H8. To see only the schematic of the cycle, this is what really happens here. This is what happens with the dome or these everything. So here 1, okay, and then 1 goes where? 0.1 will go up till 0.4. Okay, so that's 0.4. So it goes to compression processes. Okay. What happens is that, so sorry, it's not like directly on the same line. Those two compression processes are not on the same line. So first compression process from 1 to 9. Okay. Yeah. And then I have this okay, this mixing. Okay, and then from the mixing I will go again here to 0.4, and then from 0.4 I'm going to go till 0.5, and then I have here, this will stops here, this will go there to the mixing, and this will be again recirculated. Okay, it's not necessarily that this point and this point are coincident. Okay, and that's how the cycle is done. So this is 0.4, this is 0.5, this is 0.6 where we have the separation, and this is 0.7, and this is 0.8, and this is 0.3. Okay, this is 0.3. 0.3 is the point where we have the mixing or something. Where is 0.3 exactly? Okay, 1 minute. 0.3 actually is, I didn't mention 0.3 at all. So I guess 0.3 is here, the one that is here. Okay, but what happens is that we are mixing 3 with 9. Okay, so 3 with 9 are going here. Or no, we are mixing 9 and 6 and we're getting 3. And it should be that way, I believe. It should be that way. Or we're mixing 1 to 2. Where's 0.2? Okay, sorry for that. Okay, this is not 0.9. Okay, this is 0.2. So 1 to 2, this is the first one. Then 0.9 is after the mixing. So this point here in the center, this is 0.9. Okay, and 0.3 is here. Okay, so I'm mixing 0.3 with 0.2 to get 0.9. And I'm now getting this extract 7 here to go there. Okay, just memorize the layout of the cycle. Yes, so this one, this 0.7, am I giving any information? If I'm not giving any information, then I'm going to assume that it is saturated liquid as well, same as 0.5. So for 0.5, what is the information that he told me that's saturated liquid? Vapor is mixed, okay, compressed condenser by high pressure, the flash chamber, throttled evaporator, refrigerated space vaporizes the mass flow rate of the refrigerant through the lower pressure, assuming the evaporator saturated vapor. Okay. So yeah, the liquid in the flash chamber is throttled. The liquid in the flash chamber is throttled. Okay, so some of it that's taking there, and cools the refrigerated space as is evaporated in the evaporator. So this one is going to there. Okay, yes, and leaves the evaporator as saturated vapor, which is here. Now, so we have everything in our hands. Okay, it's just like you need to memorize the cycle really well. I was not memorizing it. So the rate of, or not like memorize how you are going to solve, you are just memorizing like the layout. You can understand it, like go, oh, okay, this one goes like this, like this, like this, but you need to solve fast. So that's why memorizing layout will be the best solution there. So B is the rate of the heat to move from the refrigerated space, and then I know what is H7 because I know what is this intermediate pressure. Okay, so H7, which is equal to H8, and I need H8 actually, and it is HF, okay, at that pressure, which is 450 kilopascals. So I'm going to calculate it. What is this H8 or H7? Okay, and I'm going to calculate what is H1, and I'm going to put here H8 or the higher one, okay, H1 minus H8. And I'm getting my my value. Yeah, so as simple as that. What else I need? I need the COP of this refrigerator, and also I need to determine the rate of the heat removal and the COP of this refrigerator operated on. Okay, so the COP of this refrigerator, it is going to be, okay, just don't forget this information, please. Okay, so this is not the total mass flow rate. This is going to be only an extract of it. Where you are working, you have to pay attention. If I'm working in this region, I'm going to find the first work of the first pump. So the first pump, it's also the same, this flow, it is 1 minus x6 multiplied by the total mass flow rate. If I'm working here on the second compressor, yeah, this is the total flow rate. This is the total flow rate. If I'm calculating the heat QH, yeah, this is the total flow rate. Yeah, from here to here, okay, this is the total. No, from here, starting going there, this is not the total flow rate, and this is not clearly the total flow rate. So I need the COP of this refrigerator. Now I already found QL, but I need either QH, okay, or I need the two input works here, 1 and 2. I know 0.5, but I don't know 0.4. That's the big problem. So either I should work from here, and I also know that I have an isotropic efficiency, so I have a deviation, okay, and then from here, make the mixing, 0.3, it is HF, okay, at that pressure, and 0.2, and then make mixing between them, okay, make mixing between 0.2 and 3. How you are going to make mixing between 0.2 and 3? I'm going to say that I have m dot, okay, 2, okay, so what is the m dot at 2? It's going to be x, okay, x6 m dot, okay, 1 minus x6 m dot, okay, and then multiply by h2. So this is entering, and plus here 0.3, it is going to be h3 x6 multiplied by m dot, and H3. And this is going to be equal to m dot, which is the total, because 9 here we have after the combination happens. And I can eliminate the total mass flow rate, okay, to get specific ones. So this multiplied by this, and this is H9 alone. So 1 minus X6 multiplied by H2 plus X1 multiplied by H3 is going to always give you H9. And then from H9, you're going to make an isentropic process till 0.4, okay? So make the entropy constant, and you know the pressure here, okay? And the pressure here is the same, okay? Because we are only having a mixing process, okay? I'm very sorry if this question confuses you, okay? We can do it again if you have a quiz in the refrigeration cycles, okay? But because you need to finish it, since you're going to be starting a new chapter, okay? But the idea, I think it's going to be clear for you, okay? Let's follow the solution in the manual, okay? Maybe that way it's going to be more easier for you than following with me, like using words. So close, share again. Let me share my desktop. Okay, and this is solution manual. And this is question, as we said, question 95, okay, or 59, sorry. Question 59. Okay, as we talked, H1 is Hg at that pressure, which is 200. S1, okay, that's the entropy here, nothing else. And what else we need? Yeah, so this is the first compression process. So he made the entropy constant. Okay, and then find what is H2S, and then because he have an isentropic efficiency, so he need to find H2, okay, as I told you. Now H3, this is 0.3, okay, it is going to be Hg, okay, Hg where? At the that pressure, okay, look here, we talked about it. So 0.3 is the point that is here, okay, the point that is just hitting the dome or at the saturated vapor state when you have or when you want to enter the chamber here, okay, we have also a mixing chamber here, a small one, okay, so when you want to enter this mixing chamber, this 0.3 is actually the saturated vapor state, so it is Hg, okay, that's always how it is. And then for 2, okay, so for H2 we found it already, and then H5 he told me that it is saturated liquid, so you see HF, and for 0.6 constant enthalpy, 0.7 I told you that it is HF, okay, at that pressure here. Now that one was HF at the upper pressure, this one at the intermediate pressure, okay, so you see at the intermediate pressure, HF at the intermediate pressure, which is 450, and now H8 is equal to H7, okay, are you following? Let me repeat it again, okay, H1 equal to Hg 200 kilopascals. Why? Because here it is saturated vapor, and this one is with constant entropy. I'm going up, I'm going till this pressure, the intermediate pressure, okay, so I'm fixing the entropy, going with that same pressure, finding what is H2S, using the isentropic efficiency, finding what is H2, okay, and then 0.3, which is here, as I told you, always going to be HF. Okay, so 0.3 and 7 are points that are opposite. This one at the intermediate pressure, what is Hg? This one at the intermediate pressure, what is Hf? So you see, Hf at the intermediate pressure, Hg at the intermediate pressure. Find and find. And then 0.6, okay, 0.5, it is saturated liquid, okay, because he told me that. Okay, this is not a fixed point always. This is a fixed point always. And this point, he should tell me, and this point is a fixed point always, okay? But again, sometimes he can maybe play with the givings and the unknown, so he can tell you like, no, take this one, take this one, take this one, or give you like a pressure temperature here, pressure temperature here, pressure temperature here at every point, so that you check it. And yeah, so H8 is going to be equal to H7, and H6 is going to be equal to H5. Yeah, there is nothing else. And after I want to find what is 0.9, because I want to reach this point to do to find HQL, okay? So either I need QL or the 2 pump works, okay? Let us use only the 2 pump works now for this time. So H1 I found, H2 I found after I did the isentropic, and then I used the efficiency. Now 9, as I told you, to find 9, look how it's going to find H9. M dot H9, M dot 7 H2, M dot 3 H3, M dot, this is the total one. You remember we found it 0.202. Okay, this one 0.15 because the 1 minus x6, yes, the x6 that he found before. Yeah, that's the x6 that he found before. And this one is going to be the total minus this. So you remember 0.525. We did it. Okay, we worked this part only. Yeah, as I told you. Okay, this is, and yeah. So you see, I told you either you can subtract them, or you can say that it is x6 multiplied by m dot total. Okay, either this or that. After you find what is 0.9, H9, now you are going to work and make the isentropic process from 9 to 4. Okay, so from 9, you got what is the entropy. Then make the entropy constant with 4. Then find what is H4. I know the pressure of 0.4. Use the isentropic efficiency. And then after you do it, you get now H4 actual. And now H4 minus H9, this is going to be the inlet first work. And then H2 minus H1, this is not the inlet, sorry, this is the second work. This is not the first work, H2 minus H1. You have to multiply by 1 minus x6, okay, because this is a percentage only of the flow. If you are finding specific works, multiply by 1 minus x6. If you are finding power, okay, multiply by m dot, okay. So now I'm finding specifics, and then at the end I'm going to multiply by m dot. Okay, so because now I'm finding specifics, okay, so specific in 1 is specific, it is 1 minus x6, the percentage without the m dot, h2 minus h1, of course actual, and then work in specific second, it is doesn't have this, so it is 1, the total mass flow rate, multiplied by h4 minus h9. And again, H4 actual. And then after I say like the inlet work or power is going to be m dot work in 1 plus work in 2. Or find them at the beginning as powers. Okay, directly find them as powers. So if you want to directly find them as powers, take this out, take this out. I want to find them at the beginning as powers. Okay, so here multiply by m dot, and you multiply by m dot. That's it. The only idea that I have here ratios of that total m dot. So I'm going to multiply by the ratio of that total m dot, because it's not the total m dot. So I have a ratio of 1 as before, as all the cycles that we solved before. This is a cycle where you're having like an extract, or we are taking some amount of the flow, recirculating some at a point and recirculating another at a different point. Okay, and yes, so after we make it isentropic process, everything is there. M dot 7, as you see, H1 minus H8. This one is the 1 minus X6 multiplied by total M dot, which is 0.15. And then he found, as I told you, he used the same method that I wanted to use, which is WN. So here, as you see, this is 0.15. This is not the total one. And this one is the total one, okay, which is the M dot, because from 4 to 9, it's the total. He found the network in, and then QL over the network, and this is the COP of our refrigerator. Now tells you like ignore the multi-stage cycle that we solved now. What if we have the same conditions but for normal refrigeration vapor compression cycle? Okay, so this 0.2 is going to be equivalent to which point? To 0.4. Okay, so I have here constant pressure from 2 to 3. This is the upper pressure, and this is the lower pressure, and no intermediate pressure, because we don't have multi-staging. So no intermediate pressure. So to solve this problem, it's easy. It's very easy, straightforward. From 1 to 2 isentropic process, make the isentropic line or the line of the process a bit what do you call inclined, because if we have the isentropic efficiency, and then from 2 to 3, okay, 3 is going to be saturated liquid, and then to 4 you have constant enthalpy, and then after that you find what is QL, what is work in, and this is the COP. So the multi-staging will rise the COP of my cycle. Okay. Yes. So by that, I think we've finished most of chapter 11. Okay. And the only thing that is left for us in chapter 11 is 2 questions. Okay. Just like to cover all the ideas. So those 2 questions, one of them, okay, I'm gonna just like go past them. Well, I have an idea, okay, because this question I am feeling that maybe some of you did not follow or could not follow. So I will post a detailed solution for this question, Okay, detailed solution for the third question, and a detailed solution for the heat pump question. Okay, because when you have heat pump, don't confuse yourself. It is just a heat pump. Now the COP will be different, but all the things that we did, the cycle is the same. Everything is the same. Just the COP equation is going to be different. So COP of the heat pump, it is equal to QH over work in. That's it. Or if you don't like that, so COP of the heat pump is equal to COP of the refrigerator plus 1. Okay, so find the COP as if it was a refrigerator, then add 1 at the end. Okay, so work with it normally, very normally, but it is just the difference that it is a heat pump. Okay, that's the only difference. Okay, and this question is one of the easy questions. Okay, this one is the last part of the chapter. It tells you like, now what if we are cooling using gas cycles? Okay, so it is called gas refrigeration cycles. So it is a normal Brighton cycle, okay, but now for cooling. Okay, that's it. Let's solve this one quickly, okay, and I'm gonna post for you a detailed solution for that one. So we have a gas refrigeration system using air as the working fluid and have a pressure ratio of 4. Air enters the compressor at -7 degrees. The high pressure air is cooled to 27 degrees. So now I know the Brighton cycle, okay, and I know that at first I have okay a pressure ratio of 4. Okay, so this is the higher pressure, this is the lower pressure. Okay, and here this is the pressure ratio. Okay, so pressure ratio, so pressure here, I will call this 2. Okay, I'll call this 1. So pressure 2 over pressure 1 is equal to 4. Okay, that's a fact that I know. Okay, and then he tells you that the high pressure air is cooled to 27 degrees Celsius. So this is the high pressure air. Okay, it is cooled to 27 degrees Celsius by rejecting heat to the surroundings. So here, from here to here, okay, sorry, I'm drawing the constant pressure lines as like that. This is not correct. The constant pressure lines are inclined ones in air cycles, okay? Yeah, this is correct. So now I'm following, and now what happens is that he tells me that you have a cooling of 27 degrees. Okay, but this is called the reverse Brighton cycle, so it works in reverse order. Okay, so it starts from here. Starts one is here, 2 is there, 3 is here, 4 is here, and then 1 is there. Okay, it is just like the normal Brighton cycle will be working like that. Okay, so 1. Okay, heat addition at what? At constant entropy. Okay, so heat addition, sorry, not heat addition. You have a compression at a constant entropy. Okay, so here compression at constant entropy, const S. Remember, const S. And here we have, okay, constant P, heat addition. Okay, so Qn. Okay, and then from here to here we have constant entropy. Okay, expansion. So here we have turbine. Okay, so this one is work out. Okay, and this one is work in. And then from here to here I have QL at constant pressure. So constant pressure. Same things, just now the cycle is working in the reverse order. So at first here I have the work in, which is isentropic. I have from here to here the heat rejection. So here heat rejection. Okay, because it's being cooled. Look, it's being cooled. So here heat rejection. And from here to here it is the work out. And from here to here it is the extraction. Okay, so I'm increasing the heat of the air. So this is QL. Okay, that's it. That's the principle of the reverse Brighton cycle. And he gives me everything I need. So as I told you, I have from here to here, okay, from here to here, the pressure ratio, so pressure of 2 over pressure of 1, which is also equal to the pressure of, okay, the pressure of what? Pressure of 3 over pressure of 4. Okay, yeah. So this one is equal to 4. Okay. 1 minute. I have a call. I'll be back to you in a second. Okay, yeah, so I'm back to you again. Oh, I'm not sharing my screen, or yeah, no, the screen is shared. Okay, yes. And then what we were, okay, this is 4. This is for the pressure ratio. And I have that the high pressure air is cooled to 27 degrees Celsius. So this is the high pressure air. It is cooled to 27 degrees Celsius. So this one is 27 degrees Celsius. So this is temperature of 0.3 by rejecting heat to the surrounding. And enters the compressor at -7. So here -7 degrees Celsius inlet to the compressor. And it is further cooled to -15 by regenerative cooling before it enters the turbine. So where is the turbine? The turbine should be here, okay? The high pressure air is cooled to 27 by rejecting heat to the surrounding. Okay, I have a regenerative process, okay? So this is a Brighton with regeneration, okay? No, it's not bothering a lot, okay? So you have here, this is 0.5, okay? And this is the 27 degrees Celsius. And then it also like, we have then again further cooling till we reach the turbine inlet, which is at -15 degrees Celsius. That's what he says. Okay, so this is 27. To surrounding, it is. This is further cooled to -15 by regenerative cooling before it enters the turbine. Assuming both the turbine and the compressor to be isentropic, and using constant specific heat at room temperature. So here, of course, we're gonna 5.6. Okay, and constant specific heats at room temperature determine the lowest temperature that can be obtained by this cycle, and the coefficient of performance of the cycle, and the mass. Okay, the mass flow rate of air for a refrigeration cycle of 12 kilowatts. Okay, so 12 kilowatts is clearly the input power to the cycle. Okay, and then we let me delete here. Okay, so let's work it out one step by step. So we have the lowest temperature that can be obtained by this cycle. What's the lowest temperature in the cycle? Just 0.4. So I need to work from 0.3 to 0.4. Do you have any isentropic efficiency for the turbine? Let us read. Both of them are isentropic. So 100% isentropic efficiency for the turbine and as well for the compressor. Okay, 100% isentropic efficiency. So I'm going from here to here with constant entropy. Okay, the same things are applied here. So you have cold air assumption, or if you have standard air, okay, the same thing applies. Does he said that we should ignore the specific heat, or assuming that the specific heats are constant, something like that? Let me read it again. Oh, nothing is mentioned. Okay, so let's work it using the ratios, okay, the pressure ratios and the temperature ratios, the pressure ratios and the volume ratios, assuming that they are the specific heats are varying. So at first here, I need to put what is the pressure relative of 3 over the pressure relative of 4, so that it is equal to the pressure of 4 or 3 over the pressure of 4. Okay, and I have this ratio. What is this ratio? This ratio is 4. And I have also pressure relative 3. Okay, so pressure relative 3, I have it because I have the temperature out there. That's why I have pressure relative 3. Okay, pressure relative 3, let's go to that temperature, which is -15 degrees Celsius. -15 degrees Celsius for air is equivalent to what in Kelvin? It is equivalent to 258 in kelvins. So 258, I'm going to take it at 260, okay, just for convenient. I don't want to do interpolation, but you have to do interpolation. And I am seeing that my pressure relative there, it is 0.8405. So find what is pressure relative 4. Now, pressure relative 4, after you found it, from it, you get what is temperature 4, and you get what is H4 as well, okay? Of course, we should have found H3, okay, using the temperature there. And this is the thing that's good about air, because we are only caring about the temperature. The pressure is only used in the ratios, because the tables or air tables are all function of temperature, okay? Because we're assuming that air is an ideal gas, so its enthalpy, its internal energy, its pressure relative, and its volume relative, and its specific entropy, okay, or sorry, its relative entropy are all function of temperature only. So yeah, T4, H4, and what else we need? So this I have it, okay. I want to go to point 1, okay, directly from point 4 to point 1. What I can do, I have here QL. I have the temperature here, of course, so I don't need to go in this process, or I'm bothered by this process. So directly after I find pressure relative 4, let me find it because it's easy, as you can see. So it is 0.8405. This is going to be approximately because I approximated the pressure relative. So pressure relative of 4, it is going to be 0.210. So find where is 0.210. 0.210, 0.210. 0.8. Okay, 1 minute. This is pressure relative 3. Okay, we have a pressure ratio of 4. So this is the pressure relative of 3, and this is the pressure relative of 4. 4 is at a lower pressure. It is further cooled by a regenerator, cooled to minus 15 degrees Celsius by regenerative cooling before it enters the turbine. So from here 15. Oh, it turns out that we don't have an entry for that in the table. So we don't have for 0.2. Okay. So maybe that he wants me to calculate it using the TPK relationships. Okay. Because we don't have an entry for that table. The lowest temperature that is there, it's 200 kelvins. Okay. That's the lowest temperature there. And the 200 kelvins, okay, let me see how much in Celsius is that. It is 73 degrees Celsius, okay? So the temperature is much lower than 73 degrees Celsius. It is weird. Let me check it. This question 78. Yeah, question what? Question, yeah, question 74. Question 74, what's the lowest temperature in the cycle? No, actually it's not. It is minus 49. That's the lowest temperature. Oh no. Yes, I'm correct. Yeah, it is lower than 73, which is the lowest entry, minus 73, which is the lowest entry in the table. So you have to use the TPK relationships, okay? So I just wanted to show you a demonstration, but it turns out that our temperature, okay, so here if you want to go with this pressure relative, you need other air tables. I guess I have some air tables that are going to that point, but let us use the tables that are in your textbook. Okay, so you need to use the TPK relationships now. Okay, and we know that what is the relationship for the pressure, and we need what? We need the temperature. Yes, we need the temperature. So the one that goes for that is which relation? Okay, this relation. So T4, the one that I want to find, over T1, which is minus 15 plus 273. Don't forget. Okay, is equal to which pressure? This same pressure, so the pressure of point 4, which is pressure 4 over pressure 3. Okay. And now this one is 1 over 4, not 4. Okay, and now K minus 1 over K, and you know that the K over here is 1.4. So now you find T4. So T4 is the lowest temperature in the cycle. And after you find T4, this is the lowest temperature in the cycle. What is the coefficient of performance of this cycle? Okay, so he wants the COP of this cycle, which is QL over work N. And now QL is going to be worked from where to where? Not from 4 to 1. Okay, QL is not from 4 to 1, remember. And the QH is also not from 2 to 3, because this is a regenerative Brighton. Okay, how was the regenerative Brighton working? This is the amount that you are having regeneration here. Okay, so if it was in the reversed order, that's how it was going. Okay, you have the heat here. Okay, this is the heat Q in, and this is the Q out. Okay, so it's the same thing. the same thing. From here, you have QH going out, and here this is by the regeneration. Actually, he tells you, like, look, the high pressure air is cooled to 27 by rejecting heat. So he tells you that this point is reached by rejecting heat. And further, it is cooled to minus 15 by regenerative cooling. So this region is by regeneration. And again, same thing. So this region is by extracting the heat, and this region is by the regeneration. So the regeneration is going in this direction. Okay, just like here, we have the regeneration in this direction. Okay, but the thing is that it's going from down to up or from up to down. That's the direction of the heat. Okay, yeah, let's go back to the question. So the coefficient of performance, I need to find what is 0.6 so that I can find point H. I can find it easily because I have 2, I have 5. Okay, so I can tell him that I have Cp, okay, T2 minus T5, okay, multiplied by m dot. Okay, and do I have the m dot of this cycle? No, it is not there. Okay, if it's not there, I'm gonna find the specific one, okay, without multiplying by m dot. Okay, so this is the Q dot H, and the Q dot L, it is going to be Cp, okay, T4 minus T6, okay, or T6 minus T4, depending on which one is higher, which one is lower. And to find T6, I told you, do the heat exchanger equation always. So this is a heat exchanger process, okay? So H, okay, or T6 minus T1 multiplied by Cp is equal to Cp T5 minus T3. And Cp is the same, Cp is the same, m dot is also the same. So T6 minus T1 is equal to T3 minus T5 minus T3. You have T3, you have T1, you have also T5, you don't have T6. That's the only thing that you need to find. So temperature is here minus 15, temperature is here is 27, and temperature is here is minus 7. Okay, so this is the only temperature that you don't know. Okay, and to make you follow it again, okay, because it's been a mess here and my OneNote. So where is it? How can I share again? Go here, okay, and share it in this way. Okay, no, cut the share and share, okay, and share my desktop. Okay, so you can see this was the temperature, the lowest temperature in the cycle, which is of course here. I'm just using different terminologies for the points. Okay, and now as I told you, T6 minus T4, okay, so this temperature, okay, this temperature minus which temperature? Minus this temperature is going to be equal to this, sorry, this temperature minus this temperature, so 6 minus 1 or 1 minus 6 equal to 3 minus 4 or 4 minus 3, okay, depending on which is lower. This one is higher, so 3 minus 4 and 1 minus 6, okay? So if you want to find 6, what you are going to do, you're going to take 6 to the other side, okay, and bring back 1 to that side, okay? So here we have 3, okay, it should be 3 minus 4, okay, so let me write it in the way that I wanted to do it, okay, according to the book terminology. So T3 minus T4 is equal to what? T1 minus T6, yeah? So it's equal to T1 minus T6. And I want to find T6, okay? So take T6 to the other side and bring those two to this side. So you will have T1 minus T3 plus T4 equal to T6. That's the equation. And yeah, that's correct. So this is minus 49. And now I can find everything. Now COP of the refrigeration cycle, I have the Q, the work in from 1 to 2, and which is H1, okay, so H2 minus H1, okay, that's the work in, that's the net work, sorry, that's the input work, and I need also the turbine work to subtract it, so this is the turbine work, of course, okay, H4 minus H5, okay, so to work compressor in minus work compressor out. Look at something that in reverse Brighton cycle, the work input of the compressor is higher than the work output of the turbine, because this is a refrigeration cycle, and the amount of the work that I'm getting or taking is higher because I'm doing a process that is reverse to the nature. Okay, because I am cooling, and when I'm cooling, I'm taking the temperature from the cold environment to the hotter environment, and this is against the nature. So I need to put work input. Okay, it's not like the previous cycles when you are doing Brighton for gases. Okay, So I need to produce work. Here, I'm not producing work. I need to extract heat. So that's why the work in for the compressor is higher than the work out for the turbine. Okay, so that's why you are going to subtract the turbine from the compressor, as I told you. And yeah, you are going by T's, not by H's, because this is called their assumption. So T6 minus T5, T2 minus T1 minus T4 minus T5, and then there you have it. This is the COP of this refrigeration cycle. And if you want to find the mass flow rate, then he gave you what is in the question, what is the power input of this, or the net power input of this cycle, which is 12 kilowatts here. So with this 12 kilowatts, that's what you are going to do. Okay, 12 kilowatts, and then I have here CP multiply, so I'm going to find what is my m dot. Okay, hope it was understandable for you, and as I told you, I am going to upload for you the solution of the this one, of the heat pump question, and of the cascaded, or of the multi-stage refrigeration cycle in details, so you can look at it. Okay, and these questions, please, if you don't understand anything in them or you have a point, please refer to me. And yeah, see you inshallah next time. Assalamu alaikum.